let's verify that the function u of xy equals hyperbolic sine of x times sine of y is harmonic on all of the complex plane. And then we will find its harmonic conjugate. So first, to show that it's harmonic, we have to show that the Laplacian of u, which is the sum of the pure second partial derivatives, that sum is equal to 0. So let's do that. U sub x, here's our function. The derivative with respect to x, the derivative of the hyperbolic sine is the hyperbolic cosine. So we have hyperbolic cosine of x times the constant sine of y. If we're differentiating with respect to x, then y is a constant. And so u sub xx, take the derivative of hyperbolic cosine, and that is positive hyperbolic sine. So we get back to where we started. Now let's take the derivatives with respect to y. The derivative of sine y is cosine y. So we have hyperbolic sine x cosine y, and then when we take the derivative of cosine, we get negative sine. So we get negative hyperbolic sine x sine y, and these two are clearly negatives of one another. So when we add them, we do indeed get 0, so that our function is harmonic on the whole complex plane. This equation is valid for any x and any y. Harmonic on the complex plane. So the idea of a harmonic conjugate is that if you have a harmonic function, then there exists a function f of z, which is u of xy, the given u of xy plus iv of xy, which is analytic on the set on which u is harmonic. So analytic on this set, which is all of the complex plane, which means that it's entire, to use a vocabulary word there. So we would like to find v. V is the harmonic conjugate. And we will do that by using the Cauchy-Riemann equations, which are u sub x equals v sub y and u sub y equals negative v sub x. So v sub y, we want to find v. We would like to find v of xy. And what we know is that v sub y is equal to u sub x, which we calculated here. So v sub y is equal to the hyperbolic cosine of x times the sine of y. So that's the derivative of v with respect to x. So v will be found by integrating. That was the derivative with respect to y. So v will be found by integrating with respect to y. Cosh x, which is a constant, sine y, dy. So the cosh x is a constant, and the integral of sine is negative cosine. So negative cosine y, and then plus a constant, and that constant can actually be a function of x, because x is considered a constant. Okay, so we have to finish it off, we have to figure out what possibilities we have for that constant, and we will use the other Cauchy-Riemann equation. So v sub x is supposed to equal negative u sub y, just putting the negative sign on the other side there, and that we calculated here, so that's negative hyperbolic sine x cosine y. But on the other hand, v sub x can be calculated directly from our knowledge of what v looks like. So v sub x is negative, and then cosine y is a constant, so this is just the derivative of cosh x, which is sinh x, times cosine y, plus c prime of x. So these two expressions, in order for these two expressions to be equal, we have to have that c prime of x is equal to 0, and that means c is actually a constant. C is a real constant. So the harmonic conjugate was v of xy. There's technically infinitely many of them. Adding a constant doesn't change whether a function is harmonic. So v of xy is negative cosh x cosine y plus a constant.